All right, this example comes from your text, section 5.3, number 92. The voltage in a circuit can be modeled by, and I'm going to write this equation that they have, V sub t, V is for voltage, is equal to V sub 0 e to the k t, where t is in milliseconds. So this really is the same thing or equivalent formula to PERT. Okay, so V sub t is the voltage that you have after time. So that's V sub t. That's the same thing as A. A is what you have over time. V sub 0 is your starting voltage. That's the same thing as P, your starting amount. Of course, E is the same thing. T is the same thing. And they've got K here as their rate, and we are using R. So these formulas are equivalent, so we're just going to go ahead and use PERT. So it says that the voltage decreases, part A I should say, part A says the voltage decreases by 85% in 50 milliseconds. So if I have 100% of the voltage, like think of a battery, okay, which contains electricity or can power electricity. So just think of a battery. Think of it that way. And if I lose 85% of it, that's the decrease, because I have it in my flashlight or I have something else that's being powered by it. Well, what part do I keep? I keep the 15%. So if the battery starts out with 100% power and you lose 85% of it after 5 milliseconds, you are left with 15% of it. So let's go ahead and make our chart. Volts and time. And time is in milliseconds. Okay. So when I start out, I've got 100% of the voltage at time 0. And I can think of the 100% in decimal form as 1. So then I know that 5 milliseconds later, I've lost 85% of it. Well, how much do I have left? I have 15% of it left, and of course in decimal form that would be 0.15. So the question asks me find K, and we're saying that K in their formula is the same thing as R in PERT. In other words, the rate of decline. So let's go ahead and find that using PERT. So we have 0.15 is equal to 1 times e to the r times 5. Dividing by 1, well, I don't even need to show that, dividing by 1. So 0.15 equals e to the r times 5. Solving for r, which is in the exponent, I take the natural log of both sides. So I've got the natural log of 0.15. When I take the log, I use the power property which releases the exponent, so it comes down in the front. So 5r times the ln of e. You know the ln of e is 1, so that can disappear. And I can divide both sides by 5. So let's move this up here and continue this. So r is equal to the ln of 0.15 over 5. And when you do that in your calculator, you get negative 0.3794. And you're going to keep that in your calculator because you're going to use that for part B, and you're going to do that second answer thing, which I showed you on the last example. So part B says if V sub 0 equals 4.5, well, that's really P. So P equals 4.5. So now it's saying, well, I really had 4.5 volts as opposed to over here where I just said I have 100% of volts. Now I'm actually given a certain number of volts that I have. Okay. So if P is 4.5 volts, find how many volts I have after 2.3 milliseconds. So let's use PERT. So A is equal to 4.5, because 4.5 is what I start with, e to the negative 0.3794 t. And do I know t? Oh, yes, I do. So let's get rid of that. So t I know, and t is 2.3. There we go, 2.3 milliseconds. And when you key that in, of course, don't forget to put parentheses around all of this exponent, and then your r right there, you can do with your calculator, second answer. All right, now leave that calculation up to you to do on your calculator, but do that and make sure that you get 1.88 volts. 1.88 volts. All right, so now we need to do part C. Part C is a little different. Part C says by what percent? What percent does the voltage decrease each millisecond? All right, so if you think back to when we used before we did continuous growth and decay, we had exponential growth and decay. So B, well, that's my rate of growth or decay. And in a previous example, we changed from the half-life formula to this exponential growth, and then we also changed from PERT. So we went back and forth between all three examples. So you may recall, hopefully you recall, that B, and that's the B that's in this exponential right here, that B is equal to e to the r. So go ahead and calculate B. B is equal to e to the negative 0.3794. And when you do that, you get a B of 0.6843. So what I could do here, let me erase a little bit here. So what I could do is I could make this exponential equation. There we go. I could make this exponential equation like this using B, 0.6843. And I know that this amount here, well, that's the amount or percent that is left. So in other words, this is because B is between 0 and 1. I know this is decay. So this is the amount that is left. Just like over here in this example, or this part of the example here, where I said we're decaying by 85%, we lose 85%, so we keep 15. Over here, this B is the amount that you keep. The problem is asking you by what amount does it decrease. So what you do is you take your 100% in decimal form, subtract 0.6843, see, that's your B, and then that gives you, multiplying in putting it in a percentage, that gives you 31.6%. So each millisecond I'm losing 31.6%. So I'm anticipating the question about why am I not losing 85%? Because you're losing 85% over 5 milliseconds. This 31.6%, that's per 1 millisecond. So that's one way you can do this and calculate how much you are losing every millisecond. That's the end of this example.